Welcome back to the deep dive. Today we're charting the essential blueprint for any successful AI project. We're talking about the data science methodology, or DSM.
That's right.
We're going to be looking at a structured 10-step life cycle. It was put forward by John B. Rowland, a data scientist at IBM Analytics. And the mission for you, the learner, is to really get the full picture from defining the problem all the way to deployment, without getting bogged down in the technical details.
Right, and it's so important to have that framework. It's like a GPS for your project. Without this kind of, systematic approach, teams can get lost. They might build a brilliant model that answers the completely wrong question.
Or just get stuck cleaning data forever.
Exactly. So the DSM is all about efficiency. It guides you through 5 core modules. You start with the big picture, from the problem to the approach. Then you get into the data itself, requirements to collection, and then understanding to preparation.
So only after all that groundwork do you actually start modeling.
Precisely. Then it's modeling to evaluation. And finally, you close the loop with deployment to feedback.
It sounds really comprehensive. Okay, let's unpack this. Let's start right at the beginning, at the foundation, figuring out what problem you're actually trying to solve. It seems so obvious, but I have a feeling that's where a lot of projects go wrong.
You absolutely hit the nail on the head. Step 1 is business understanding. And this is where projects fail. So often, you see teams perfectly solving the wrong problem. It's critical because this step sets the entire business context. It defines your objective.
Measurable objective.
The measurable objective, yeah. It has to support the customer's goal. It involves really intensive problem scoping. You might use tools like the 5W1H.
The who, what, where, when, why, how.
Exactly. Or even concepts from design thinking. The whole point is to make sure you understand the root challenge, not just a symptom. If you can't state the problem clearly in one sentence, you are not done with step 1.
Okay, that brings us to our example for today. Imagine a man named Pavan Sankar at a huge food festival. He's got some health restrictions, so he needs to avoid certain types of cuisines. But the problem is the dishes are just listed by name, not categorized.
Right. Total chaos.
So his business problem, or his personal objective here, it isn't just find food. It's very specific. It's identify the cuisine type like Thai, Mexican, Indian for every single dish so I can filter them.
Yeah.
Defining that before you even think about data is business understanding.
And that clarity immediately points you to step 2, the analytic approach. Once you know the objective, the data scientist can choose the best way to answer it. And this is a big decision point. Are you trying to categorize something? If so, that's a classification problem. Or are you trying to predict a number, like how much or how many? That's regression.
Classification versus regression. Got it. But I've also heard there are like 4 main types of analysis that really set the direction for a project.
Correct. And these 4 types tell us what kind of knowledge we're trying to create. We usually start with the simplest one, descriptive analytics. This just answers the question, what happened?
So looking backwards.
Purely looking backwards. It's just summarizing historical data. Think about a basic sales trend chart or a financial report. It tells the CEO, we lost $1 million last quarter.
Okay, so it's the rearview mirror analysis. It's just stating the facts.
Precisely. Then you can level up to diagnostic analytics. So if descriptive tells you what happened, diagnostic asks, why did it happen?
Ah, okay. The next logical question.
Right. This is where you drill down, you look for correlations, for root causes. Maybe that $1 million loss was tied to a very specific and very unsuccessful marketing campaign. Then we get to the really exciting stuff, predictive analytics. This uses all those historical patterns to forecast what will happen. This is where you see machine learning models predicting, say, stock prices or future customer demand.
And then the highest level of all.
That would be prescriptive analytics. It goes one step further and answers, how do we solve it? It's not just predicting something bad will happen, it's recommending the best course of action to prevent it. It gives you actionable advice.
Okay, so if we go back to Pavan at the food festival, he's trying to categorize an unknown dish into a known cuisine type. He is squarely in the domain of classification, which falls under predictive analytics. We know the approach. So where do we get the raw materials?
That moves us perfectly into the data handling module, starting with step 3, data requirements. You know the question. Now you have to define the specific information you need to answer it. What types of data? What format does it need to be in?
And I imagine this is where a team decides if they need structured, unstructured, or maybe semi-structured data.
Absolutely. Do you need a nice, clean table that's structured data? Or do you need unstructured data, like text from social media posts or images of the food? Or maybe something in between, semi-structured, like an email where the key info is buried in the text? For Pavan, his requirement is simple. He needs a list of ingredients for every dish.
Which brings us to step 4, data collection. You've got your shopping list. Now you have to go get the stuff. How is that data sourced?
Generally from one of two places, a primary source or a secondary source. A primary source is raw, original data you collect yourself. You run a survey, you make an observation. For Pavan, it might mean literally going to each food vendor and asking for the ingredient list.
A lot of work.
A ton of work, but you have maximum control. The alternative is a secondary source. This is data that's already been collected and is ready to use. Think of data from the WHO or public government data sets. For Pavan, this could be finding a huge online database of recipes already tagged by cuisine.
Much faster, but you're relying on someone else's work.
Exactly. You're at the mercy of their quality and structure.
So once we have Pavan's ingredient data, maybe a mix of notes from vendors, and that online database, we hit step 5, data understanding. This feels like the moment of truth.
It really is. It's the initial investigation, the sniff test. You use descriptive stats. You use visualizations like histograms just to see what you've got. Do we have way more data for one cuisine than another? Is there a huge bias? Are there obvious gaps? You spot these big picture issues right here.
I remember working with a database where the date was entered in like 12 different formats. That is the pain of step 5 leading right into step 6.
That pain is so real. And that brings us to step 6, data preparation. And, everyone says this is the most time-consuming part. It can be 70, even 80% of a project's timeline. It's the deep, hard labor of cleaning and transforming data.
So if it's 80% of the work, is that a sign something's wrong, or is that just the reality of messy real-world data?
That is just the reality. Data in the wild is dirty. You're handling invalid values, removing duplicates, trying to figure out what to do with missing data. But the really strategic, I'd almost say artistic, part of this step is feature engineering.
Okay, let's spend a minute on that because it sounds like where the real insight comes from.
It truly is. Feature engineering is the creative process of selecting, modifying, or even creating brand new features, new variables, from the raw data to make your model better.
So you're making the inputs more meaningful.
Exactly. Think about a classic example, predicting house prices. You might have a raw data point, year built, say, 1975. That number on its own doesn't mean a whole lot to an algorithm, but if you engineer a new feature, age of the house, by just subtracting the year built from the current year, suddenly you have an input that's way more predictive.
And for Pavan and his ingredients.
For Pavan, instead of feeding the model a long, raw list of ingredients, he might engineer features like count of specific spices or a simple yes-no for presence of dairy. He could create a feature called contains coconut milk, which would be a huge clue for classifying Southeast Asian food. That transformation just makes the model so much smarter.
That makes perfect sense. Okay, the data is clean, it's structured, it's expertly engineered. Now we get to the heart of it. Modeling and evaluation. We're at step 7.
Right, this is where we start testing our hypotheses. And it's a very iterative process. You rarely just pick one algorithm and it works perfectly. A data scientist is going to test a bunch of them, linear regression, decision trees, neural networks, to find what fits the problem best.
And the models, as we said, are either descriptive or predictive.
Correct. Descriptive modeling would be to summarize patterns, maybe show Pavan the 3 ingredients most correlated with Thai food. But predictive modeling is what he really needs to forecast the cuisine of a new, unseen dish.
So before we get to the final deployment, we have to talk about model validation. Why is this so critical? You built the model, why not just use it?
Because you need to know if it's actually any good. Validation is how you check that your model can generalize to new, unseen data. It's the check against a problem we call overfitting, where the model just memorizes the data you trained it on. A model that can't handle new data is, well, it's worthless.
And the standard way to do this is the train test split.
That's the first one everyone learns. You split your data set into a training set, maybe 70 or 80% of the data to teach the model. And you keep the other 20 or 30%, the test set, completely hidden. You only use it at the very end to get an honest evaluation of its performance.
But what if you have a small data set? Splitting off 30% might not leave you enough data to train the model properly.
An excellent point. And that's exactly where keyfold cross-validation comes in. Instead of one split, you divide the data into, say, 5 equal parts or folds. Then you train and test the model 5 separate times. Each time, you hold out a different fold for testing and use the other 4 for training.
So every piece of data gets to be in the test set at some point.
Exactly. It gives you a much more robust and stable measure of your model's quality, especially when you don't have a ton of data to work with.